So I posted for you online the first lecture with learning glass. I don't know, did you see it or not? I wish that you like it. I don't know. We'll see. We're gonna post today the two lectures. Lecture two from this Zoom meeting, which is about 2 hours. But also I'm gonna post the learning glass, which is also would be much faster to cover everything in like half an hour or so. So today we're going to finish the last lecture section, which is 1.4. We did not define something called phase. Phase is exactly like phase. This is the end of 1.4. Phase. What is phase, guys? Is a quantity of a matter that is homogeneous throughout. Quantity of matter that is homogeneous. For example, if I give you a cup of water and everything here is water, so this is what? Pure liquid water. If I decrease the temperature below 0 Celsius at 1 atmosphere, it will be ice. Yes, this is water and this is water, but this is solid state, this is liquid state. If I heat it up, it will be vapor, water vapor, more than 100 degrees Celsius at ambient atmosphere. So all of them, phases are water. So phase is quantity of a matter that is homogeneous throughout. What does it mean? Let's say I get some water liquid and liquid some ice. So I have both, some liquid and some ice. This is ice. This is liquid. All of them are water. For example, this is called two phase. So we have here one substance here. Here is single phase. Here is single phase. Here is single phase. But here is another phase, which is single phase also. So anything in this domain is single phase until you get here. This is called two phase between the ice and the liquid. The same if we have vapor. If you have liquid, some liquid, and you have some vapor. Here is one phase, here is one phase, but this is multi-phase, two phase or more, we call it multi-phase. So a quantity of matter that is homogeneous throughout the system. Okay? Any question? Guys, any question? Can anyone hear me? Say yes, no.
Yes, we can hear you.
Great, great. So everything is clear, as I mean, everything is fine. That's it. Great. So, of course, the properties may a little bit change, but still we have almost same properties. We can say pressure, we can say, for example, volume, mass, temperature, everything we used before for a phase, we can apply it for any of these phases. So here, when I cool down below 0 degree, here below 0 degree, here heat up more than 100 degrees Celsius at the room temperature, at ambient pressure, heat, it changed the phase. It can be partial reversed. We're gonna take this problem in details in the very end of our lecture. So let's go now to section 1.6. Section 1.6. Which is start with state. A state, guys, state, it's set of properties. Set of properties. Let's say I have cup of water. I say give you mass, volume, temperature, pressure, density, whatever, any property here, like if you have entropy, if you have energy, anything I give it for you, this is called a state. Let's say state 1. We used to use circle 1 or just state 1 or S1 or A, anything, that's called state. So it's a substance with a set of properties. So maybe you can say a substance. Can he say here? A substance with set of properties. That is a state. That is what? A state. We have a very, very important rule. It's called state postulate. That's very important. You will see it in the midterms, in quizzes, and even in the final. It's called state postulate. What is that? I don't care if any of you have background of thermodynamics. We gave everything by definition from the beginning. What a state postulate is? In a very simple word, you can say like this. The state, I can say it first, then I will describe it. The state of a simple compressed fluid is completely defined or described or known to completely, everything is known. Everything is known by two independent intensive properties. What is this? Two independent. What is this? What does it mean? Okay, I'll describe it for you. First of all, we describe property can be extensive or intensive. Intensive, independent of the size of the system. So we define something called intensive property. So here, mass extensive, volume extensive, temperature intensive, pressure intensive, density intensive, entropy. If it's a specific entropy, intense, a specific energy, a specific volume will be intensive. Would be intensive. So we have some properties are intensive, and some other are extensive. If I give you two independent intensive property, let's say, for example, temperature and volume, a specific volume, sorry. If I give volume, it's not actually extensive. I cannot give you volume itself. I need to give you something intensive, independent of the size. If I give you these two, you have everything. You can get pressure, entropy, energy. You can get anything for this state. So the state is completely defined. It's completely defined. It needs to be independent. Some intensive property dependent. For example, if I give you rho and nu, they are dependent. A specific volume and density, they are dependent. I cannot give you here, for example, I cannot give you rho and nu. That's dependent property. They are the same. So I need to give you two independent, two things, any two things. For example, if I said I want to talk to Marco, you cannot get it. One name, or Marco, whatever, Marco Gonzalez, I cannot talk to him. But if I give his name and his address, I can reach for this guy, correct? So I can reach this student or this guy. So I need two things. If I give address, a lot of people in this address, but I need to get two, I need to have two independent intensive properties. Let's say I give you, for example, T and rho. If I ask you for pressure for this gas, so you can simply say P equal rho RT. So you have two independent intensive property, you get the third. If I want energy, it's a CVT. Internal energy or internal energy CVT, total energy or enthalpy CVT. We're gonna take these details later. But for example, from two independent intensive property, you get the third, pressure. equation of state, or equation gas law. We can get enthalpy. We're going to define this later. Energy, anything you want for this system, you can define by just any two. Not any two. Independent, intensive. Independent, intensive properties. Hey guys, so far so good. Any questions? Any question, guys?
No, so far so good.
For everybody, what will happen? We'll have data like table or a chart. Maybe, let's say I'm gonna plot T versus rho, for example, for now. A lot of things here, a lot of things, a lot of curves. If I give you two independent intensive properties, for example, temperature and density, you can get exactly everything. You will see a constant pressure line. You will see a constant entropy line. You will see constant enthalpy line. You see a lot of things. So you can get the whole state. This is state one. From two independent intensive properties, I can get everything about this state. Pressure, we're gonna do it later. So now, the state postulate says, a state of simple compressed fluid, any compressed fluid, liquid or gas, is completely defined by two independent intensive property. Remember this forever. This is the most important keyword in thermodynamics. Two independent intensive property. It means two properties, they are not related. They are not cousins like this. They are not related to each other. They are not married. Okay? Okay. I assume that everyone is following me and the voice is clear. Okay, let's go now to lecture 2. This is in the lectures, you will find this is lecture 2, thermodynamics, ENGR 130. So today is June 26, 2020. We're gonna keep going. Now, section 1.7. We're talking about equilibrium. You know equilibrium? The movie 202, 2002? No, it's not. This is called imbalance. The word equilibrium means they are in balance. If I give you 1 kilogram like copper and 1 kilogram of air, they are in the balance, they are the same mass. 1 kilogram, 1 kilogram. Maybe the volume of the air is huge, almost 1 meter cube, and the volume of copper is so small, look less than like a size of a liter, but they are in balance. So we have something called thermal equilibrium. From now on, EQU, it's equilibrium. Sometimes EQI, sometimes EQIL. So this is the typical equilibrium abbreviation. You will see a lot of temp. It means temperature. Pressure. Equili, it means equilibrium. EQ, equation. When you see this word, it means equation. Equilibrium. You have here pressure, temperature. And this is A. This is U. Okay, some keywords you see. Thermal equilibrium means temperature is the same throughout the system. So here, temperature is the same throughout a system. So this system is in thermal equilibrium. Thermodynamics only deal with thermal equilibrium states, only. If you have non-thermal equilibrium states, it's not thermodynamics. For example, if I give you a cup of water, it has water, let's say 25 Celsius, and you put some ice. This ice was negative 15 Celsius, some ice. This is, before you put ice, in thermal equilibrium. This is, yes. This is called a state. I can consider it a thermodynamic problem. I can solve it. In the moment when I put the ice, so you have some part has negative 15, some part at 25, and they are reaching equilibrium. This is getting warmer, this is getting colder, warmer, colder. Now it is not anymore thermal equilibrium. In the moment you put the ice in the water, it is not thermodynamic problem. So before it was thermodynamic, yes. When you put, it's not thermodynamic problem. It's a non-equilibrium. This is getting colder, this is getting warmer. When they reach equilibrium, let's say everything became like 5 Celsius. This is now a thermodynamic problem. So this is thermodynamic problem. This is thermodynamic problem. Thermal equilibrium. Everything, temperature is the same throughout the system. Temperature is the same throughout the system. But here is not. This is not thermal equilibrium. This is not thermodynamic problem. Then we're going to define, this is equilibrium, thermal equilibrium. Then we're going to define, if somebody take notes, please be faster. I wish that everyone take notes, everybody. Some of these notes are not already in the lecture. You need to both look at both and also take notes. The more you take, the better it is. Like I write the notes almost 3 times. When I read the book, I write down. When I summarize it in your notes, I write it a second time. Now this is the 3rd time. That's almost, I remember everything because of repeating it a lot. Now we're gonna define something called, I forgot what we're gonna define now. Process, then cycle. So process, what is process? Now I said thermal equilibrium is a state, something we are interested in. So we have a state. Then it's gonna go to another state, like the problem I mentioned like a few minutes ago. The water 25 became 5 Celsius. This is called process. This is called process. So a system undergo from one state to another. It was in one state means equilibrium state to another equilibrium state. From one equilibrium state, if you want to write it correctly, from one equilibrium state to another. From one equilibrium state to another. This is called process. For example, if I give you a piston cylinder, and here you have control volume, like this. So we have temperature, we have pressure, we have specific volume, we have a lot of intensive properties. And I compress this, I compress that. So this is thermal equilibrium. I will call it, for example, state 1. It has certain temperature, certain pressure, certain specific volume. So if I compressed it, what will happen? If I compressed it, this volume will be smaller. The same mass is the same, but now here this is state 2. Again, thermal equilibrium. Thermal equilibrium. We have another, let's say this is T1, P1, V1, specific volume 1. This is T2, P2, V2. So here the temperature increases, we compress gas, temperature increases, pressure increases, specific volume decreases. Let's say now I'm gonna plot it in let's say T diagram. So this state 1, pressure increases, temperature increases. So look like state 2 will be here, something like this. This is called path. So I'm going from state 1 to state 2. Property A, property B, any two properties, pressure, temperature, volume, any two properties. I can draw like this from state 1 to state 2. This is called a process from one thermal equilibrium to another. Low temperature, low pressure, high specific volume, to low temperature, high pressure, high temperature, but lower specific volume. So if you plot this plot, the same plot, for example, between PV, it was actually here, 1. So the pressure increases, yeah, I'm going to go up, but the volume decreases, I'm going to go lower. So it's look like here, something like this. And this is the path, the direction of the process. We don't care much about paths, but now we have state 1 and state 2. Because here the pressure increases, I'm sure I'm going to go up. The volume decreases, I'm sure I'm going to go left. So it's here in this quarter or this place. But here the pressure increases, of course. The temperature increases, so I'm sure here. What the path look like? This is called the definition of process. Before we go to cycle, let's take some example of process. Let's take some examples of process like what? We have a very important word, it's called iso. Iso means the same. Iso means the same. So we have isothermal, iso something, isothermal, isochoric. This is one word. Isobaric. Sometimes we say isometric. What this isothermal, isochoric, isothermal means? What does it mean? They are something is constant between two states. Here, the thermal is constant, which means temperature is the same. So here this means T1 equal T2. So if you're going from state 1 to state 2, isothermally, it means temperature is the same. Isochorically or isometrically, it means specific volume is the same, or at least volume. If you're going isobarically, it means pressure is the same. Then we're going to do isentropically, which means entropy is the same. Something is constant through a process. This is called iso something. Something is constant through a process. Iso something. Thermal, constant the same. Choric, it means this is one word, guys, not two words. This is isochoric, one word. Isobaric, one word. So something is constant through a process. Iso something. Isothermal, isochoric, isobaric. If you have any question, guys, please write it down. I see a lot of chat. Let me stop now 1 sec to see what happened to the chat. 1 minute. It's a gun. Cup of water, it's a gun. So you need to get a clue from you need to decode what I'm writing. And you have notes. It's matter, yeah? Okay, I think some of you are answering the question. That's very good, very, very good. I'm happy to see that. Please do that, yeah. I'm focusing on the lecture, so if somebody is not saying something and you can hear it, because I say what I write, so most probably you hear it, so you can say it for somebody else. So we start with equilibrium, something in balance, thermal equilibrium, which is all the thermodynamic problems must be in thermal equilibrium. Process, system go from one equilibrium state to another. This is called a process. We have some example of process, something like isothermal, isochoric, isobaric, isometric, which means the volume is the same. Let's go to the next one, which is cycle. What is cycle? When the system, you have a system, and you return it back to original initial state, this is called a cycle. Let's say you return it back this to its original place, exactly original place. This is called a cycle. So when a system returns to its initial state, equilibrium state. When a system returns to its initial state, it is a cycle. This is cycle, guys, by the way. See why? It is a cycle. Like, let's say you have here state 1 here. Somebody compressed, expand, do more expansion, burning, something like this. I go from 1 to 2, 2 to 3. These are 1 to 2 is what? Is a process. Another process, another process, another process. If I return it back to original position, this is called a cycle. Any two properties, A and B. If I did not return, like this, 1, 2, 3, 4, maybe 5. As long as I do not return it back to original initial state, it's not a cycle. I need to go back, like let's say from 5 to 1. I can have many processes, 2, 3, 4, 5. It's supposed to be more than 2. Like 1, go back and forth. This at least 2. So you have 1, 2, maybe 3. Like 1, 2, go back to 1. Or 1, 2, 3, 4. So we can have a lot of processes, but we're going back to the initial state. That's called a cycle. In this course, we're going to get a lot of cycles. By the end of the chapter 9 and 10 and 11, we're going to learn about Otto cycle, diesel cycle, Brighton cycle, a lot of beautiful cycles, a lot of very beautiful cycles. You're going to apply everything here in a real system. You see isothermal, isochoric, isometric. You will see that all of these special words, you're going to apply them in a real problem. In the jet engine airplane, you will see how much thrust you can get from the jet engine by just applying these simple, beautiful things. Okay? So maybe the last definition, which is, it's a logical definition, which is called steady state. Steady state means no change with time. There is nothing change with time. There is nothing temporal in the problem. So when I see state 1, I don't care what the time is. I don't care what the time is. So these are steady states. There is nothing related to time. Okay? We're gonna jump to some definition in chapter 2, like energy, internal energy, kinetic energy. Then we go back to some definition here, temperature and pressure. Then we're gonna continue to our very interesting part in the lecture. So I'm gonna stop here for chapter 1. This is still lecture 2. Then I go a little bit definition in chapter 2 first, which is energy. We have a lot of forms of energy. So what is energy is, guys? Start with 2.1. Energy is the ability to cause a change. The ability to cause a change. So energy, in the exam, if I ask what the energy is, simply energy is the ability to cause a change. Mathematically, energy equal F times distance, force times distance. In SI units, joule, Newton meter. So the ability to cause a change. That's why the kids have a lot of energy. We all know that in this pandemic, because of they are home, there is no school anymore. So you know what is energy of the kids are. So this is the ability to make change. A lot of change in our life. A lot of things broken in our home. That's called energy. They have a lot of stored energy. We have a lot of forms of energy. For example, we have mechanical energy. We have chemical energy. We have nuclear energy. Oops. We have potential energy. We have one of the mechanical kinetic energy. They are all energies. We have magnetic energy. Two magnetic poles can attract each other or repulse. This is energy. We have chemical, nuclear, potential. We have electrical energy. Electrical energy. All of them are energies. And most importantly, the kids' energy. That's maybe you don't know. These are the form of energy in the book. If I were them, I'll write kids. I'm a big kid like this. My son and my daughter. So we have a lot of forms of energy. Okay, that's not related to you guys. Okay, so we have, for example, in this course, we care about potential energy. Let's look around the color. We care about potential energy, kinetic energy, and it's something called internal energy. I'm gonna write it down. Let's say here internal energy. Come on. So we have a lot of formulas, but we care about 1, 2, and 3. These are the most 3 important things. I'm gonna describe them. So let's start with potential energy. So we use the symbol PE. What is potential energy, guys? mgz, and z is elevation from the datum. So this is the Earth. If you go with altitude z, you have here potential energy, mgz. This energy is extensive property. Like if you have this pin here in this altitude, it has energy. If I leave it, it will drop down. It loses its energy, transforms to kinetic energy. So this is a very famous problem, free fall. You have here potential energy. When I leave the pin, it will fall down. The velocity increases. It was 0, increases until it became maximum before it touched the ground. This energy depends on the size because I have mass. If I want it to be independent of the size, what should I do, guys? I need a specific potential energy. Hi, guys, what should I do? Somebody tell me.
Do you divide it by the mass?
Perfect, exactly. We're gonna use a small letter, PE equal GZ. That's it. This is a very beautiful trick to transfer any extensive property to be an intensive, independent of the size of the system. Regardless what you drop, if it's an elephant, if it's a pen, if it's like a needle, they are the same potential, specific potential energy, GZ. There is no mass. All of them GZ. Okay, guys? A specific potential energy. Let's talk about the next one. Take a blue. Kinetic energy. What is kinetic energy, guys? K capital, E capital. Any capital from now on is extensive, is total, is regarded to the system. Defined for this system because it has mass. This V small is velocity, but V capital like this, it's a volume. This is from now on our notations, our nomenclatures in this course or any course, most probably. This energy will need to be specific, independent of the size. So we're gonna use a specific kinetic energy. We're gonna use K small, E small. Everything is small from now on would be specific. It means half V square. Oops, half V square. We have something called internal energy. I'm gonna use this. This is a very important internal energy. Something very, very, very important. We use the symbol U. So U is the summation of all internal energies. U, the summation of all internal energy, like what? Like, for example, nuclear energy. For example, molecular energy, molecular. For example, this pencil here, yeah, as you see, it's rigid, but actually it's a lot of molecules, and all of them are vibrating. If the vibration is very fast, temperature is high, for example. If the temperature is low, it's very cold. So this pencil, however, you see it's solid, but it has a lot of movement of the molecules. This total energy, we call it U. It most probably represents temperature. For now, assume it's a temperature times something. So we have a specific internal energy, which is U small. Okay, so we have potential energy, kinetic energy, and internal energy for system. Extensive property. We have a specific potential energy, a specific kinetic energy, a specific internal energy, kinetic internal energy, which is independent of the size of the system. Okay. If we ignore the rest of energies for our systems, if we ignore all the other energies, we will have in our system, we don't have, oh, here. Let's talk total energy. Let's say it is E. In the book, we use E. The total energy. Internal or external? Internal energy, everything inside the system. Not like potential, not like kinetic, not like, for example, magnetic, not electric. We neglect everything else. Maybe we can put these two inside here, guys, but it's okay. For now, total energy like this. It is U plus KE plus PE. They are constant as long as I did not add anything. Can you see this pen, guys? Can you see this brown? Is it clear, this pencil, this marker?
Yeah, I can see.
Okay, total energy is E capital equal U capital, internal energy plus kinetic energy. If you have other energy, add it. If you have energy, add it. As long as the fluid or even a solid have this energy, it's not going to change. As long as nothing happened. For example, this pencil, it has this plus this the same. When I drop it, potential energy transfers to kinetic energy. Correct? But if there is a friction with air, it gets some of the energy. Let's say it gets warmed up. So some of the energy goes to the heat. So not all the energy go to kinetic energy. This energy is constant as long as there is nothing added to the system or removed. For fluid, solid, anything. We have a specific total energy, which is E small equal U small plus key E small plus key P, PE small. So it's then total specific total energy is E small. Is specific internal energy plus a specific kinetic energy plus specific potential energy. Okay, guys, any questions? Any question, guys? I see some comments here. Any question, guys? I'm assuming there is no questions. Okay. I am not that good, by the way. So if you have a question, you can ask, no problem. I'm not going to ask that, but ask a question. Feel free to ask it. Okay. Okay. So we talk about energies, and it takes a lot of energy from me to describe this. I get tired. Let me get some coffee. Actually, this was 2.1 and 2.2. I forgot to write it. Okay, anyway. We're going to go back actually to the 1.8. I think this is, I don't see. This is 1.8, yes. 1.8. Now, let's go to 1.8. Section 1.8, which is about temperature. We were in 2.1 and 2.2. Now we are in 1.8 back. This was about energy. Now we go back to define temperature. Now we can easily define temperature. So temperature is a measurement, for hotness or coldness of a system. It is actually molecular energy. Like if you have this pencil, this marker, whatever this marker is. This marker, guys, has in temperature, let's say 25 Celsius. It has a lot of billions and billions of molecules. These molecules are vibrating. This vibration is temperature. If it's very fast, temperature getting warmer, and it means it's warmer. If it's very slow, it's getting colder, even minus 20 or 50 or 100 Celsius. It means it's getting slower, it's getting colder. So hotness or coldness, something we can feel from a system. It's not energy yet. We need to do something to be an energy. So temperature is a measure of how hot or how cold it is, but it does not mean energy yet. It does not mean energy yet. So we define actually a thermal equilibrium based on this temperature. Thermal equilibrium means temperature is the same. So the hotness or coldness is the same everywhere. The same molecular dynamic energy everywhere in the system, fluid, liquid, solid, gas. So let's define the zeros law. We define a little bit the first law, which is energy can either be created or destroyed, but it can transform from one form to another. We define the second law of thermodynamics, which is a measurement of disorder and the direction of the process. But we're gonna define them later in chapter 4, 5, and 6, and 7. A lot of repetition in details. First law of thermodynamics, open system. First law of thermodynamics, closed system. Now we're gonna talk about zeros law of thermodynamics. This is zeros law. Maybe the start with first law and second law. They found something obvious. They call it zeros law. So obvious, something so obvious, which is like this. I have two markers here. Let's say two bodies, A and B. A in thermal equilibrium with body C. B in thermal equilibrium with body C. If A and B, each one of them in thermal equilibrium with third body, like A in thermal equilibrium with C, B in thermal equilibrium with C. This means these are in thermal equilibrium, A and B. If two bodies in thermal equilibrium with a third body, if A and B, A in thermal equilibrium with C, B in thermal equilibrium with C, two bodies in thermal equilibrium with a third body. This means, so these bodies, these two bodies are, of course, in thermal equilibrium. Let's take an example. Let's say A is a ball of iron or steel. Its temperature 50 Celsius. This is a water. If it's thermal equilibrium with this, it means 50 Celsius. So this, put it here, nothing will happen. This is 50 Celsius ball, put it here, it will remain 50 Celsius everywhere. This is another ball, another metal, in 50 Celsius also. If I put it here, it means in thermal equilibrium. But if it's 40, no, it's not thermal equilibrium anymore. It needs to be the same temperature to be in the same thermal equilibrium. So if I put B here, yeah, nothing will happen. This 50 degree remain 50 degree, this 50 degree remains 50 degree. This means these two bodies are, anyone will say that's obvious. That's why it's zeros law. Okay? It's so obvious. Clear? Everything is clear, guys?
Yes.
So temperature. Let's go into temperature, how we measure temperature. What the scale, what the value. There are 4 bad guys, scientists. No, they are good guys. They are scientists. They are very good guys. Celsius, Kelvin, Fahrenheit, and Rankine. So these are, again, 2 units. We have SI units, we have British units. For SI units, somebody is named Celsius. He said, I'm going to measure the temperature. He got water, and he cooled it down until it freezes at 1 atmosphere. He used 1 atmosphere as reference. And he cooled it down until it became ice, completely ice. When it started to be ice, he called it 0 Celsius. When he heated up at 1 atmosphere until the first vapor started to show up, he called it 100 Celsius. For example, our body temperature is 37, something in between. So our body, human body, in this grade, 37. He can do something else. He can do from 0 to 200. So we can be 40 or 60 or 72, 74. So he can do another measurement. But he said, okay, let's do this scale from 0 to 100. He can make it 0 to 1. It will be very hard to us. He can do anything. He used 0 and 100. Actually, I think I missed S. Celsius. So this guy, his name is Celsius. He take the water as a reference and he froze it and warm it up. And he called this Celsius. He's a bad guy. Remember that forever. So another guy is called Kelvin. Can I use Kelvin? You know Kelvin? Home Alone? So Kelvin, not Kevin, Kelvin, another scientist, he did something very important and very good. Very, very important. This is the most important scale you will have for temperature in your life. Kelvin scale. He said, okay, this is wrong. Or I have another scale much better than this, which is the kinetic energy, molecular energy. He said, this 0 actually is not 0. It's actually 273.15. So the water freezes, the water freezes at the water boils at, but this is at 1 atmosphere, should be 1 atmosphere. If you have another pressure, if you have different, okay, let's take a 10-minute break. We're gonna come back at 11. I'm gonna stop now. I'm gonna continue from here. Okay, 10-minute break. Take rest from me. See you guys. Hey guys, I assume you're still alive. It was me. So alive online. I mean, not alive. So I'm gonna start now. So we get set temperature we have SI units, we have Brent units. SI units, we have Celsius. Scientists, he said water freezes at 0 degrees Celsius, water boils at 100 degrees Celsius. Kelvin said, no. I'm gonna do the same thing. Let's say water freezes at this and boils at 373.15. But he gave something very, very important, which is 0 Kelvin. This is impossible state, impossible to happen. 0 Kelvin means there is no molecular motion. I give you a pen, every molecule is frozen. It's impossible. Here you feel it's solid, but it's still vibrating, it's still moving. Every molecule is vibrating, every atom is moving. The electrons is moving around the nucleus. So everything is moving. 0 Kelvin, there is no movement. It's impossible. It's impossible. Negative degrees here still moving, but with negative with respect to. But 0 here, it means there is no movement. Absolute 0, it never ever happened. When you go from here to there, transformation is simple. T in Kelvin is exactly T in Celsius plus 273.15. So 0 here means 273.15. 100 here means 373.15. So the transformation from Kelvin to Celsius. Let's go to the bridge we are using here in the United States. Fahrenheit mean. Fahrenheit did the same thing. He said, oh, water freezes at, can somebody tell me what degree? Does anyone know? Fahrenheit temperature, water freezes at what temperature? Anyone? You are all American. Hey guys.
32.
Perfect. 32. Boils 212. So this is exactly the same. Water freezes at 32, boils at 212, which means T Fahrenheit equal 9/5. T in Celsius plus what? Plus what? 32. 0 here means 32 Fahrenheit. Put 100 times 9/5 plus 32 is 212. This is a very important relation. Do not memorize. Just know there is something like this. Try to practice a lot, but try to not. Of course, if you practice a lot, you're going to memorize it yourself, like me, but do not memorize it for objective of memorizing. Try just apply. If you have Celsius, you can get Fahrenheit. If you have Fahrenheit, you get Celsius, and so on. Rankine is the absolute temperature in that. This is the important for SI. This is the important in bridge. Is a T Rankine is T in Fahrenheit plus 459.5, I think. Let me check. Yes, 0.7. This is 7. That's what I expect. Okay, so if you have Celsius, you can go Kelvin. If you have Celsius, you can go Fahrenheit. If you have Fahrenheit, you can go Rankine. So if I give you this, I want Kelvin. From Rankine, you can get Fahrenheit. From Fahrenheit, you can get Celsius. From Celsius, you can get Kelvin, and so on. So Rankine is the most important thing in bridge. Kelvin is the most important thing in SI. So if I give temperature equal 30 Celsius, has no value. I don't care. I need the Kelvin, which is 300.15, for example, or 303. Like this Kelvin. This is important. Yeah, this is correct. After you got Kelvin, this is important. Do not use ever Celsius. Always use Kelvin. Okay, now let's go to the next section, which was 1.9, last section in chapter 1. Are you alive? Come here. So 1.9. So we have pressure. Pressure is so important in fluid mechanics, of course. Pressure, 1.9, is force per unit area. Force per unit area. The body force per unit area. For example, we are living in atmosphere. The atmosphere, which is, let's say, this is you. My daughter can draw better than me, by the way. I'm sorry. This is you. Sabaiki. So this is you. You have above your shoulder a column of air until the end of the atmospheric pressure. This column, the weight, which is force per unit area, is 101325 Pascal. Everybody almost carry above his shoulder 100 kilopascal. Everyone, pressure is in our sea level is almost 100 kilopascal. Okay, 100 kilopascal, like almost 101 kilopascal. This is force per unit area. Let's take another example. Like low pressure, very simply, is force per unit area. We have force in Newton in SI, meter square. So this is Newton per meter square or Pascal. P capital is small, Pascal. The scientists we're gonna use now, we're gonna define now Pascal principle. Let's take a simple example about pressure or stress in general. You know, when you want to cut an apple, you have a knife. Let's say this is a section of a knife, something like this. Why you cut from here, not from there? From sharp edge, not this. Why? Do you know why? Because of the definition of pressure. So pressure is force per unit area. You go to the minimum area to apply as minimum force as possible to get the same pressure. Actually, if you cut by this, you can get the same pressure, but you need huge force. So the area is so large, you need huge force to get the same stress. So when you get a knife, you of course you cut from the sharp edge because it's easier. The sharper the minimum area is, the larger the pressure is with the same force. So this is the definition. We are subconsciously do a lot of things naturally. We are doing it without any even thinking. Of course I'm gonna do with the sharp edge because it's minimum force. But you know that? Have you ever, when you cut something P equal F over A? Have you done that, guys? I do sometimes. I do that sometimes. Yes, I said that we are crazy. I said that. So P equal F over A. Pressure have 4 or 3 famous scales. Vacuum, we have absolute. Let's start from the beginning. Absolute pressure, vacuum pressure, and we have gauge pressure. 3 pressure, 3 scales. There is a different pressure, it's okay. Just focus about these 3. The first one, a difference, it's okay. Like Rho GH, it's a difference pressure. We care about absolute, vacuum, and gauge. Actually, we care about absolute and little bit gauge. Vacuum, we don't care much. What is absolute? Let's say this is the datum. This is the ambient, the space. The space is 0 Pascal. If you are outside in the space, there is no pressure, there is no fluid. So you have 0 Pascal, absolute 0. There is no pressure. When you have fluid, you have pressure. More fluid, more pressure. Like our atmospheric pressure, atmospheric domain. This is pressure. When you go deep in the water, it's more pressure. It's impossible to be negative. It's how? It's either you have force or not, absolute force on you or not. So this pressure, there is nothing called negative absolute pressure. The space is 0 pressure. Now, if you go now, measure the pressure. Let's say, for example, 10 kilopascal or more, or whatever. This is called absolute pressure. So this is a pressure from vacuum or space. The pressure from vacuum. We measure the pressure from the vacuum, above vacuum, 0 Pascal. If you measure pressure until, for example, almost 100 kilopascal, 100 kilopascal. This is approximately 1 atmosphere. This is called 1 atmosphere, for example. Now, the gauge pressure is the measurement from here. So from this one, this is P gauge or PG. Is P absolute minus P atmosphere. So if you have this pressure, in absolute, you have 10 Pascal. So this point, let's say here, P1, let's say this one, equal 10 kilopascal. This is what? Absolute pressure. It's also equal to P1 gauge, which is negative almost 90 kilopascal. So B1 absolute is 10 kilopascal. I can measure from here 10 or from here negative 90. So the B gauge is exactly, B gauge is B absolute minus B atmosphere. You are putting air in your tire. Your tire. So the tire, if you have here, let's imagine that this is the tire. This is cross section. The pressure inside, if it's 1 atmosphere, and here is 1 atmosphere, you read 0 gauge pressure. If you put the gauge, there is nothing. It's totally flat. When you add pressure, build up pressure inside. So pressure now is 1.1 atmosphere. You measure by gauge 0.1 atmosphere. Pressure outside is 1 atmosphere. Inside 1.1. This is absolute pressure, but this is gauge pressure. You read P gauge. Okay. pressure is so important, guys. It's so important. I will show you a video right now about pressure, how the pressure is significant, important. A vacuum is exactly negative of this. P vacuum is negative B gauge, which is B atmosphere minus P absolute. It's actually measure. I can use another color better. Let me use another color, blue. B vacuum is making as B gauge. It's exactly P atmosphere minus P absolute. It means you are measuring from here P vacuum. So this point is 10 kilopascal absolute, negative 90 gauge, positive 90 vacuum. This point, 10 kilopascal absolute, negative 90 gauge, equal P vacuum, which is 1. It's positive 90. Measure from here. So the gauge upward, the vacuum downward. That's it. These are the three. We're not going to use much of vacuum, just the definition. We're not going to use even much of gauge. We're going to use it some, but we care about absolute. We care about the absolute from here. Measure from here, from zero, from a space. Let's watch a video. Share screen. Can you see now the video?
Yes.
Yeah.
Okay. This is a tank. Can you see the tank, guys? This tank can sustain at a very, very high pressure, correct? Like maybe 100 atmosphere, some of them 10 atmosphere so easily. We're gonna apply negative pressure, negative gauge. Can you see?
Yeah, we can see it.
Did you see the force?
Yeah, we did.
That's implosion. It's inverse to explosion. So this is how big the negative pressure is. It can damage something designed inappropriately. This design can sustain for 10 atmosphere. Like you can go here 10 atmosphere, 100 atmosphere. But when you go negative gauge pressure, like of course absolute pressure is positive, like 50 or even 20 or 30. If you go to this below, it can implode. It can go inside each other, like this implosion you saw in the video. Okay. There are a lot of examples. You can watch a lot of examples about how the inappropriate design can cause unbelievable damage. And of course, we have rho GH, which is a pressure difference. Like if you go deep in the water, it's a rho GH. We're going to take an example similar now. Let's go now talk about the Pascal principle. And Pascal principle is so simple. You know, you heard it many times. This is from high school, Pascal principle, like Archimedes principle. The pressure throughout applied to a confined fluid, increase pressure throughout the system. It's a very famous problem. This is a hydraulic jack, a very famous problem. If you confined, totally confined, there is no air, completely confined water, for example, everywhere, completely confined fluid. If you add pressure here, you get the same pressure here. If you add pressure here, you get the same thing here. This is called, the pressure is the same throughout the system. Pressure here, the same as here, the same as everywhere. So P1 equal P2, which is F1 over A1 equal F2 over A2. This is hydraulic jet. Hydraulic jack. A very famous problem. This is hydraulic. Hydraulic. Okay, hydraulic jack. So the pressure here, exactly same as here. So if you move this a little bit more with a very small force, actually here is bigger force, here is huge force. So force per unit area is the same. So area small, force small. Area big, force big. The pressure is the same throughout this. So we use it a lot of problem. I'm sure you have heard this and saw it many times. It's called Pascal principle. Let's take two problems. I'm gonna give one of them. It's problem 54. Problem 54 in the textbook. 154 in edition 8. It has equivalent in edition 7. It's a girl. She want to do skating in the ice, and she is girl. She has a weight, a mass. The mass given 70 kilogram. She want to skate in the ice that only sustain at maximum pressure of 0.5 kilopascal, about 500 pascal. It means the ice will broke of the gauge pressure. So this girl need to wear shoes here with area. This shoes has area, 2 shoes. So we have 2 areas. So the pressure, by definition, force per unit area. The pressure maximum I have. So what happened? I need to get the minimum area needed to get this pressure. Of course, if the area is bigger, that's better. When you have bigger area like this, it's better. The bigger the area, the better the skating board, the stability is, because you distribute the weight a bigger area, so it's less pressure. So we are below the maximum. The bigger the area, the better. So we need the minimum area. So the force here, very simply, is just mg over area. So the mass 70 kilogram. The acceleration 9.81 meter per second square. It's if you are talking about SI, 9.81. If you're talking about bridge, it's 32 feet per second square. The area, that's what I want. Actually, here we have 2 areas. Area 2 shoe. 2 shoes. So the pressure, we need 0.5 kilopascal. It means 1,000 pascal. So we have 1 is 1. We have K, we have M, we have G, we have T, and so on. This means, like if you're talking about 1 meter. Kilometer is 1,000 meter. Mega is million. Giga, billion. Tera, 1,000 billion. If you're talking about milli, the same for weight. If this is, for example, gram, the same thing. If you're talking about anything. Millimeter, we have -3. Macron, 1 over million. Nano, 9. Pico, femto, or second, or anything. Sometimes we need these scales. This is standards. Like femtoseconds, very famous. Okay? So this is the scale we use in our fluid mechanics, in our solid mechanics, in our physics. So usually here uppercase letter K, M, G, T, lowercase, sometimes Latin or English. Okay. So this is kilopascal, 500 Pascal. If you simplify it, I think I gave it by 2a. I did not get the a. It's 0.457 meter square. You can divide by 2. 0.687. Look, 687, 687, 687. So you try to double check the ratio. Now, let's. This is a problem 54. Problem 58. It was about barometer. You know barometer? Barometer is a device to measure ambient pressure. It has 76 millimeter mercury. This 76 millimeter mercury is equivalent to 101,325 Pascal. 101,325 Pascal. Now let's go back to chapter 2. Let's go now. This 1.9 is over. Let's go now 2.3. About pure substance. 2.2. Pure substance. What is pure substance? Pure substance is a substance with fixed chemical composition. In the exam, I'll ask you this simple question. I'll give you a cup of water and ice. Water liquid and ice. Is this pure substance or not? Guys, yes or no? Which one is correct? True or false?
It's true.
Exactly. The chemical composition is the same. Everything is H2O, ice, vapor, water. If you have 3 of them, all of them have the same chemical composition. But the answer is simply yes, true. If you don't have any other impurities, this is the same fixed chemical composition. Yes, it's different phase. Yes, multi-phase. Yes, but pure substance. Something is pure. Unlike my coffee. Okay. Yeah, it's very hot. This is isolated. You see, you are crazy. Okay, guys. Where were we? So of course, if you do not laugh, you're gonna get 0. So remember always to laugh. Even I cannot
Funny.
assume that. You're gonna get bonus, guy. Okay, let's go to this.
Wow.
So pure substance. What? No, not everyone. The first one laugh. That's it. Okay, let's go this. So we said a substance can keep you pure or not pure. Let's take a very interesting problem. A very, very interesting problem. Something you will like it a lot. This is the most interesting part in the whole class. I promise you. We're gonna derive everything in the steam table. So focus with me with this 20 minutes or so, please. We have, I give you ice, some ice at negative 15, 20 Celsius. And we're gonna draw heat, maybe versus temperature. That's good. Heat versus temperature. So I give you ice, let's say at negative 15 Celsius. Focus with me, please. This is heat, A, state A. It's a pure ice, negative 15 Celsius. At what atmosphere? 1, everything here is 1 atmosphere, for example, for now. Then I asked you to add heat. We add more heat. Volcano, we add heat under this. So what happened? This will go like this. Temperature increases, heat increases. Yes, correct. Until certain degree, which is 0 Celsius. Guys, this is 1 atmosphere. Pure ice, pure water, pure substance. It means it can be water, yes, but I mean it pure. It does not have any impurity. It does not have salt, sugar. It does not have any other chemical composition. If I add at 1 atmosphere, add heat, temperature increases. With thermometer, yes, temperature increases until 0. At 0, temperature will not increase. I'm adding heat, guys. I'm adding heat. Temperature doesn't increase. You know why? Because at this point, liquid starts to show up. So this is ice, solid. At this point, we here have complete liquid. So it's complete liquid in this cup, complete liquid at 1 atmosphere. But the temperature is 0. So I'm adding heat, but temperature doesn't change. I'm adding heat, temperature doesn't change. Temperature is the same. So do not always stick heat, it means temperature. No, it's not necessary. This process is isothermal between B and C. Isothermal, temperature does not change. Temperature does not change. We call it fusion. We have evaporation and fusion. So it was complete ice, became complete liquid from B to C. We add heat, we add energy, but I do not see any temperature. It's impossible. If you can be able to measure 0.1 C, I give you $100. Okay? I'm gonna get you $1. I'm gonna be rich if you do that a lot. So this is always 0 Celsius, no matter what. Not negative, no positive. It's 0 perfect Celsius. The definition of Celsius is here. So when I add more heat, yeah, now it's gonna temperature increase. Yes, perfect. Until, for example, D. What is D? 100 Celsius. And 100 Celsius, vapor starts to show up. Remember, I'm fixing 1 atmosphere. I have pure water. Pure water. Ice, ice and liquid, liquid, liquid and vapor. So at this point, we have complete vapor. Temperature remain 100 Celsius, and it's impossible to add more, 0.1 or less, 0.1, as long as you have 1 atmosphere and pure liquid, pure material. So here, vapor. Now, this is superheated vapor. This process is called evaporation. From D to E, isothermal. It is actually isothermal because temperature is constant. Pressure is 1 atmosphere. If I told you the pressure is larger, like for example 2 atmosphere, you will find the same curve. Let's draw it for you with this, I don't know, pink maybe. It will find like this at 15 Celsius, like this. What is this? You need higher temperature to melt, higher temperature to evaporate. This is 2 atmosphere. Let's give you lower pressure. Let's say yellow. You need lower temperature to evaporate. Lower temperature to melt and evaporate. This is 0.5 atmosphere. That's beautiful. Do you like it, guys?
Yes, it's good.
So this thing is called the steam table. Look at this. This is the steam table. Let's draw it again with different variables. We have P, T, and V. Can you pick up 2 variables, guys? Anyone pick up 2 variables? I will do it. T and V. Let's say P and V. Let's say P and T. If you want any 2, yeah, all of them. Do you like it? Can you see, guys, this part? In the left? In the left? In the left?
It's blurry.
What? You can see it?
You can't really see it. It's blurry.
Okay, let's take another color. I'm gonna do another color, big color. Let's this one. This is here. So look at this. I'm gonna start like C, like this C. 1 atmosphere. If I'm here, this is what happened here. This is 1 atmosphere. Follow me. 1 atmosphere, I was here. Like let's say 15 Celsius, liquid. Liquid. Do you know what is this? Somebody can tell me what this is? Value? Huh? Anyone tell me this value? What is this? Almost at room temperature, you have 0.001 meter cubic kilogram for water. This almost liter of water, it has almost 1 kilogram. Almost. If it's 1 kilogram, it means it's 0.001 meter cubic kilogram. It's a liter. Exactly liter. Correct? This point, it does not change much. That's why we called it incompressible fluid. Here, incompressible. It's a complete incompressible fluid. So this number is the most important number in your life. This from here to here is almost the same. You can find here it's 0.00105, for example. It's almost the same. At this point here, for example, it's 0.00105 or 11, like almost nothing. Much even lower, maybe 0.05. This point, at 1 atmosphere, water start to boil at 100 Celsius. So what happened? If you wrote TV or PV, let's start with PV better. TV is very good. TV. And this is constant pressure line, 1 atmosphere, 1 atmosphere. The volume is almost the same, and I'm keep adding heat, recording temperature and volume. So I got 1 liter of water, and I keep adding heat, recording this, recording that. At certain point, the water start evaporate until become complete vapor here. This point, everything is vapor. Here, it's vapor but getting warmer. The same pressure. So let's say like this. Imagine this design. This is a piston here. I'm putting some water here. I'm adding heat. And this piston free to move. This is 1 atmosphere. So here 1 atmosphere. When I get more heat, more expand. More heat, more expand. So it's getting bigger and bigger and bigger, but still, as long as this is free motion, this is 1 atmosphere always. Because it's free motion. This is 1 atmosphere, 1 atmosphere. It's free to move. I'm adding heat, expand. I'm adding heat, expand, expand. I'm recording temperature, pressure, temperature. Pressure is the same, sorry. Temperature, volume, temperature, volume, temperature, volume, temperature, volume, temperature, volume. Here, isothermal, isobaric. From complete liquid to complete vapor. Almost the volume does not change. I want you to remember this number, please, forever. When you see this number, this is exactly like this. Exactly like this. On 1 liter of water. Yeah, I get it color. Now I'm here, like about, I think 40. This one. Okay, it was here now. Like, I don't know. My wife gave it to me here. It's boiling. Like I'm getting burned. So here, getting warmer, record the volume and the temperature, specific volume and temperature. At 1 atmosphere. Guys, this is 1 atmosphere. If I want to plot the same thing at 2 atmosphere, what do you think? Above or below? I need, if I add here, force here, make it 2 atmosphere and free to move. I'm adding pressure to the system. I'm trying to compress it more. It's hard to escape. It's hard to. So what happened? The green line, it starts like this. It needs higher temperature, let's say 120 degrees, until to boil. Then like this, then like this. Here, everything is liquid. Here, everything is vapor. Here, mixture. Okay, so here is liquid. Here is vapor. Okay, let's talk about 0.5 atmosphere. 0.5 atmosphere. I'm gonna use the red line. Can you see, guys, this chart? Yes or no? Guys, can you see?
Yes.
Okay, great, great. So what happened? This is 0.5 atmosphere. I need lower temperature, maybe 60 degrees or something. 6 degrees, for example, here to boil, for example. This is 0.5 atmosphere. The green one is 2 atmosphere. Somebody very smart draw 2 lines. Connect all this line together. This line here. This line there. Sorry. And he called this saturated liquid. And that saturated vapor. It's here completely liquid. Here is completely vapor. This point is called critical point. This is in the exam. Of course, this is in almost every exam, midterm and final. This one, we have 3 regions, 2 lines, 1 point. 3 regions, 2 lines, 1 point. 3 regions, subcooled, compressed liquid, subcooled, always liquid. Saturated mixture, superheated vapor, superheated vapor. Everything liquid, mixture, vapor. Liquid, mixture, vapor. Liquid, mixture, vapor. 3 regions, subcooled. Region 1, cellular mixture. Region 2, superheated vapor. Region 3. 2 lines, saturated liquid, saturated vapor. Saturated liquid, saturated vapor. 1 point, critical point. 3 regions, 2 lines, 1 point. In every exam, I ask you, draw for me the 3 regions, 2 lines, critical point, 1 atmosphere, 2 atmosphere, half atmosphere, constant entropy line, for example, constant volume. Where is the constant volume here? Do you know where is the constant volume line? Can somebody tell me where is the constant volume line? Guys, where is the constant specific volume line? It's one word. Vertically. This point, for example, is exactly 1.67 meter cube per kilogram. It means I started with 0.001 meter cube per kilogram. I start with this small space. It's almost this one. 1 liter. When I keep add heat, it expand. It almost 2 meter cube. Almost 2 meter cube. 1.767 meter cube per kilogram. This line is V equal 1.67. Like if you have any in math, X and Y. This is called Y equal 3. This is called Y equal 0. This is called X equal 0. X equal 3. X equal 9, 5. The vertical line on axis is X equal this. That's why this point, we call it 3 or 5 and 3. X equal 3, Y equal X equal 5, Y equal 3. Correct? This is coordinates. So this line is a constant specific volume line. Here, any vertical line is a constant specific volume. Any line, constant temperature line. Temperature here is 15 Celsius. Here is 100 Celsius, 120. Every point here is 120. Correct? So horizontal lines, constant temperature line. Let's take this line, for example, 100 Celsius. Can you see this line, guys? This line?
Yeah.
This line is called 100 Celsius, correct?
Yes.
Stuck this star. Okay, look at this line. I'm gonna draw it here in a T. Let's say, can you see this one? I'm gonna draw it here better. This is the last thing in this lecture. Let's draw now the, for example, PV diagram. PV diagram. In PV diagram, let's start with constant temperature line. Let's say this 100 Celsius. I took point 1, 2, 3, 4, 5. It's like this. Point 1 is here. Point 2 is here. Point 3 is here. Point 3 is here. Point 4 is here. Why? It's very simple, guys. Look, the pressure this line is 2 atmosphere, 200 kilopascal. So it's high pressure. Then I go to low pressure. Then constant pressure. Then lower pressure, 0.5 atmosphere. So here high pressure, correct? This point high pressure. Does anyone agree with me? This is high pressure, 2 atmosphere? Yes or no?
Yes.
Yes, it's here. High pressure, 2 atmosphere. This point, 1 atmosphere. Here, 1 atmosphere. It remains 1 atmosphere. 1 atmosphere. Isobaric or isothermal. Here. Then when I go, still I'm having 100 Celsius. This is 100 Celsius line. This is constant temperature line. Temperature equal 100 Celsius. I took this line. When I plot it here, it was broken line like this. Exactly like that. Again, we have subcooled, saturated mixture, superheated vapor. 2 lines, saturated liquid, saturated vapor. Critical point. 3 regions, 2 lines, 1 point. 3 regions, 2 lines, 1 point. Here, 3 regions. Two lines, we're gonna see them, and 1 point. Let's talk another constant temperature. Let's say this line, 15 Celsius or 50 Celsius, 50. Here, this is 50. It goes from high pressure, low pressure until constant pressure. Then when you go out, lower pressure. So it's of course high pressure, constant pressure, lower pressure. This is 60 Celsius, for example. If you want, I'm gonna draw it with another color for you. So always like this. Maybe this one, yeah. Here. This is, for example, what? 60 Celsius. High pressure. When you expand it, make the volume bigger, temperature is constant, the pressure decreases. The same pressure, then expand, lower pressure. If we connect these points, we create 2 lines. 2 lines, saturated liquid, saturated vapor, critical point. Here, if I ask you an exam, draw for me TV, constant volume, constant temperature, constant pressure. PV, constant temperature, constant pressure, constant volume, saturated liquid, saturated vapor, critical point, 3 regions, 2 line, 1 point. 3 regions, 2 lines, 1 point. Any concern? Any problem, guys? Any problems? If you have any problem, let me know now, please. Do you have any question? Guys? Everything is
No
good?
questions.
Everything is
good. No
good?
questions. Yeah.
Are you sure? So you are saying I'm good, professor? I don't
Yeah.
think so. Anyway, so this is over now. This almost 11:50. So let's talk Monday. Monday, I'm gonna make a post for you for the book if you're interested. Yeah, see you guys. Bye bye. Bye bye.